Hi there, welcome to the presentation on power, on physics, and as you can see from this very beautiful, incomplete, rather bad diagram. This is supposed to be a golf glove, a boxing glove, and also here another boxing glove, and this is a muscle. And as you can see, this is the reason why you probably see the reason why I have not done art as my main degree. I don't know what that line is supposed to be. And anyway, so power is really defined as the amount of energy per unit time, amount of energy converted, or amount of energy transferred per unit time, and it's also thought of as the amount of work done in an amount of time. So this guy with that big muscle, he can probably do a lot of work in a short amount of time. So you can look at power as work done divided by time, or energy transferred divided by time. And so to use a lot of energy is not enough to be powerful. You've got to do it in a short amount of time. That's what the definition in physics of power, and it doesn't have so much to do really with this type of strong guy. It's got more to do with transfers of energy from one place to another, etc. So I'm gonna go ahead and delete this guy so it doesn't distract you so much. It's in its pathetic glory. And so let's come up with a proper, more serious yeah, more serious definition of power. Power is the rate of doing work, and or it can also be thought of as the rate at which energy is transferred. Okay, so these two are both ideas that have to do with well, they're exactly equivalent to power. So these are really the two main ways of thinking about power. And we'll come across a lot of situations where we use this idea of power, and one of them, this one here, rate at which energy is transferred, is, for example, if you have an electric circuit and you have a bulb plugged to the circuit, and the power of the bulb is the rate at which energy is being transferred to the light bulb, and that will have a pretty direct relationship with how bright the bulb shines. So therefore, bulbs and electrical appliances have a rating in terms of watts. The watts, which are the units of power, they come as a main sort of way of measuring how much electrical consumption of energy is going to be involved with that appliance. Hopefully that makes the idea of power more in the context of what we've been talking about so far, which is work done, things moving, forces pushing, velocities, and things like that. Things like that. So power is defined by the equation power equals work done over time, as I mentioned already, or also energy transferred over time. And we also looked at the notion that the work done is the same thing as the energy transferred. They are the same thing as one another, really. Perhaps slightly different ways of thinking about the same thing. And the letters, the way you would normally express this, power is given the letter P, which is convenient, and you can say that the work done is written like this, for example, delta W. I wrote it as energy W last time as a type of energy, but it's probably more appropriate to use this W here, which is what they use in most textbooks. So delta W divided by T. and that's equal to the delta energy divided by T, and this way we distinguish between energy and work done. Even though with a subscript you can also do it, but it's the same, doesn't really matter. Okay, so yeah, I would recommend the W. Units normally used for work done, since it's a type of energy, is always the joule, which is written like that, the joule, and the letter is the J. Energy, or energy transferred, energy also has the same unit, the joule. Time is obviously got the units of time, which are sorry for the silly sentence, the units of seconds, and power has the units of watts, which are written like that, and it's a W. So really, if power is equal to the work done divided by time, or the energy transferred divided by time, then that's the same thing as saying that the unit of power, which is watts, is equal to joules per second, or joules second to the minus 1. So hopefully that makes sense. So now let's talk a little bit about the relationship between power and velocity. Power, change color here, power and velocity. If a steady body makes a steady force, so if a steady force, emphasis on the word steady, means the same as a constant force, makes a body move with uniform velocity, then you're in luck, because if they ask you to calculate the power, then you can say, well, it's a constant force, so that's going to be easy. The power is the work done, let me stick to the same notation, the work done divided by the time, and since the work done is the same thing as the force times the distance applied, then we have force times distance or displacement divided by time, and as we know, displacement divided by time is the same thing as velocity, so we can just say that this is force times velocity. Right, I did this step here to show that you know, whenever you multiply a whole number like that times a fraction, hopefully you know that this is the same thing as multiplying the force divided by 1 times the fraction. The top multiplies with the top, F delta S, and the 1 multiplies with the T, and you still get T. So therefore I can, instead of going from here to there, I can go in the other direction. I can go from F delta S over T to F times brackets delta S over T. These two are exactly the same mathematical expressions, so then I can look at this and say, well, that's just velocity. So my force times velocity is going to be the power, so that's a really convenient thing. We can either think about it as the work done divided by the time, or even the question they say there's a car that is going forwards with a velocity of 20 meters per second, and that's a constant velocity, and the force of the engine is 200 newtons, and it keeps on putting force, which is a constant force, so therefore there has to be a resistance, because if this is a constant velocity, then the resistance needs to be the same as the driving force. If the driving force is 200, then the resistance force would also have to be 200. But anyway, they don't have to tell us that in the question, but we just need to know that. Then if 200 newtons is acting in that direction as a constant force for 20 at a velocity of 20 meters per second, then we know that the power would just be 20 times 200. So 10 times 200 would be 2000, so 20 would be 4000. 4000 watts, right? Or joules per second, or joules second to the minus 1, but always give power in watts if you can. So hopefully that makes sense. Now we'll do other videos which are more focused on examples, and these are more to do with theory and understanding, so we'll leave that for another time. Now this is therefore a really important equation that you've got to learn, and I'm gonna put it here in big. Power is equal to force times velocity. Very important to know that. And this is going to be in the case of a steady force, so that's really important, a steady force or a constant force. Okay, if the force is changing, then we can't really use this for the power unless it's changing completely steadily, and then the force goes from this value to that value, and you can take the average force by doing F1 plus F2 and then divided by 2 to get the average force, and then that times the average velocity could give you the average power. Okay, but that's not normally a question that you would get, but yeah, normally you use this when the force is a constant. Now let's think about the unit of the watt to see what a watt is. So if power is energy over time, then we can say, well, and let's say what the joule was. So it's joules, so power is watts, and that's the same thing as joules per second, right? But the joule energy, the joule was equal to the joule we got from half mv squared the last time we did it. So a half mv squared would be m would be kilograms, v squared would be meters per second squared, so meters squared seconds squared, and then here we got to do all of this, which is the joule times seconds to the minus 1. So really we end up with kilogram meters squared seconds to the minus 3, because these indices add. Minus 2 minus plus minus 1 is minus 3. So this is the units for watts. So the base units for the watt. Hopefully that makes sense. Okay, so don't have very much time left, but I want to mention quickly the idea of efficiency. And power output efficiency is normally measured as efficiency means mechanical systems are, you know, they're never 100% efficient. So an energy is always lost to thermal energy, sound energy, and all sorts of stuff like that. So normally we can calculate the efficiency as the work output, so how much work you actually get out of the system. You divide that by the work that you put into the system, and this is always going to be smaller than the input because some of it is lost. So you put in so much and you get a bit less out, and then if you divide one by the other you get the fraction, and if you multiply that by 100 you get a percentage efficiency. Okay, efficiency. And you can do the same thing with energy, so energy input divided by energy output, and you will get the same ratio, energy output divided by energy input, and you will get exactly the same ratio if you multiply that by 100 as the this one here, percentage efficiency. Also you get it with both of these, because work done is energy per unit time, and the time is at the top of the fraction and at the bottom. So if you do divide energy by time at the top and energy by time at the bottom, you get the same thing as if you just divide energy by energy. So these two are equivalent exactly. So just to mention that, perhaps that's a bit counterintuitive, but the work done is just energy over time, right? So if we do this for the energy output and we divide that by the energy input divided by time, that's the same thing as here, just doing that divided by that, because the time here, if we multiply top and bottom of this fraction by the time, they disappear. So really we get the same fraction here and there. So you can do it with work or with energy and you'll get the efficiency either way. Okay, out divided by in times 100. That'll tell you how efficient the system is. So I hope that power makes a little bit more sense now, and we'll do some videos with examples, and then you'll really get the grips of it. Alright, thanks for watching. See you in the next video.